There. So I've started to record, and let me first start with, let's see, I've got so many different things to show you. I'm not sure what to start with. So let me go to the top of this. So I've got two examples from chapter 7 and a couple from chapter 6. Maybe I should do some of the ones from chapter 6 first. So let me see if this was the only one I was thinking of doing from chapter 6. I should have made myself a roadmap of this. Yeah, I guess I better just go here. All right, so you can see the screen here, and what I'm showing you, let's look at the top part of this screen for the moment. And what I'm showing you is the square root of x plus iy for the case in which the cut is on the negative real axis. So I think this is something worth going through in a little bit of detail. Now, what you notice is, what does it mean if the cut's on the negative real axis? Well, then, if x plus iy is this blue point here, then the square root, well, it goes over here, so that it halves the angle. So this is the original angle. It's something like, I don't know, let us say in degrees, it's something like 150 degrees. Well, it gets cut to something at 75 degrees, and if this is a long distance, it gets to be the square root of this distance, and so it becomes here. I haven't said what 1 is on this axis, so I'm not sure whether things get bigger or smaller. The square root of a half is bigger than a half. The square root of 2 is smaller than 2. Anyway, if it's in the upper half plane, it gets moved over there. If it's in the lower half plane, well, suppose it's down here. Well, the angle gets halved. And over here, the angle gets halved again, the angle gets halved. And so this point shifts over to here, this point shifts over to there, this one to there. So all the real part of the square root of any complex number is positive or non-negative if you put the cut of the square root function on the negative real axis. And so let me then go through the derivation of problem 31 of chapter 6. So what we see here is that we can set the square root of x plus iy to be alpha plus I beta, with alpha and beta both positive. And what we can see is that we can write it. The point here is, let's see, I didn't say something to you. The imaginary part of the square root has the same sign as the imaginary part of the number. In other words, if z is x plus iy, the imaginary part is y. If y is positive, it stays positive. If y is negative, it stays negative if the cut's on the negative real axis. So then we can write the square root of x plus iy as a positive alpha, positive beta, and then a ratio of y over absolute value of y. That means it has the same sign. The imaginary part of the square root of x plus iy has the same sign as y. And so this is the picture, and these are the equations, namely, this is equal to alpha plus I, y, beta over absolute value of y with alpha and beta positive. Well, if you square this equation, what you get is, it turns out that you get x is equal to alpha squared minus beta squared, and you get the absolute value of y is 2 alpha beta. So then in this equation, you substitute for beta. Beta is y, absolute value of y over 2 alpha. You stick that in there, and then you have an equation involving alpha squared and 1 over alpha squared and x. And, oh, I see, I didn't do that. What I did was apparently I made an equation for y. So I substituted for, right, no, what I said was right. We're going to substitute. Boy, now I've gotten myself completely confused here. The equations are x is alpha. Maybe I should do this in the first case. So first case would be this picture, the cut over here. Then what we've got is that x is equal to, well, let's do the whole thing. We square, we get x plus I, y is equal to, and when we square that, we get alpha squared minus beta squared, and the imaginary part is 2i alpha beta y over absolute value of y. And so then we get the equations, of course, that x is equal to alpha squared minus beta squared, and y is equal to 2 alpha beta over, oh no, it's 1, sorry, hold on. Let me bring out my, oh God, Jiffy eraser. And so this is then 1 equals this over absolute value of y. So the equation is absolute value of y is 2 alpha beta. And now you can solve this equation. So if we make this, what we have is we can say that, let me see, what are we solving for? I've actually gotten a little bit confused. I want an equation with just alpha and y in it. And well, I'm going to just set beta equal to absolute value of y over 2 alpha. And so then I have the equation x is alpha squared minus beta squared, which is alpha squared minus y squared over 4 alpha squared equals x. Somehow I am missing something here. I thought this was just obvious and straightforward, and I'm a little confused. Somebody may see what I'm doing wrong. Multiplying through by alpha squared, we have alpha to the 4th plus minus, that's a minus, so let me just fix this last thing, minus x minus x alpha squared minus y squared over 4 equals 0. So that's the equation I'm getting. God, that's no use at all, is it? Well, I must say, I've gotten myself a little confused here. If you solve these resulting equations correctly, what you get is that alpha is this, namely the square root of the square root of x squared plus y squared plus x over 2, and beta is that. And then when you got those both positive numbers, the expression we had was alpha plus iy, beta over absolute value of y, and then substituting, you get that. This by construction then gives us that the real part is automatically positive, and the imaginary part has the same sign as y. So that's how that works. And I must say, there's either a misprint or I'm missing something here. Let's now go to the other case where the cut is on the positive real axis. Well, if the cut's on the positive real axis, then points up here go like that. You have the angle. The angle is sort of 45 degrees, it goes down to 20. Here the angle's around 110, it goes down to, I don't know, 60 or something. On the other hand, if the angle is almost 2 pi, it goes into almost pi. And if it's something like this red dot here, it goes to this red dot there. So the upshot is, in this particular case, the upshot is that the imaginary part of the square root of z is always positive. You see all these points wind up in the upper half plane. And on the other hand, if y was originally in the upper half plane, then the real part of the square root is positive. And so let me give you one more example of that. So I'm trying to find a different color to use. I'll use yellow. So in other words, if there was a point here where what would that go to? That would go to a point basically over here. And so the imaginary part of the square root is always positive, and the real part has the same sign as the imaginary part of z. So here the yellow, blue, and black points were all had the imaginary part of y positive, and they all wind up in the right half plane. On the other hand, the ones that started out, the red and the green dots, start out in the lower half plane, and they wind up in the upper half plane. So the imaginary part of the square root is always positive, but they wind up in the left side. That is to say, the real part has the same sign as the imaginary part of z. Anyway, once you've done that, then you see that you can express square root of z as something positive, but something that will have the same sign as y, and then I times something positive. And now if you square these and solve for alpha and beta, what you find is this, and I'm not going to screw around with those two equations again, because I've gotten confused now twice, and I don't want to waste class time trying to get that straight. I'm sure you can solve those equations. I thought here I would solve, I would do another problem here in this chapter 6. And the question is, well, this was an example. What is I to the I? Well, first of all, what is I in general? Well, I is e to the I pi over 2. Whoops, hold on. E to the I pi over 2, but we can multiply it by any equivalent representation of 1, namely e to the 2 pi ni, where n is an integer. So I is e to the I pi over 2 plus 2 pi n. So I to the I is e to the I times pi over 2 plus 2 pi n. And this is equal to e to the minus pi over 2 minus 2 pi n. So you see, originally, this, let me just get rid of this. This 2 pi ni is completely innocuous when you write I, but when you take I to the I, it makes a difference. And now I see it's actually more complicated than that, because when you say I to the I, you see this extra I here is actually more complicated. So it really isn't what I said. It's actually, I to the I is actually, it's the original expression, but then we multiply that by I. And so that means it's e to the original I, which is pi over 2 plus 2 pi n. And now we multiply that by I, but we use the more general form, which is e to the I pi over 2 plus 2 pi n. Right. And actually, the answer I originally gave was correct. So in fact, you see this thing here, e to the I 2 pi n, that just comes out to be, so this is just what I said it was. So there wasn't any mistake there. Let me get back to this. So it's actually this one, e to the I squared pi over 2 plus 2 pi n, which is, as I said, e to the minus pi over 2 minus 2 pi n. So the original, as I was saying earlier, the original, let me just get the original e to the 2 pi ni looks completely innocuous, but when you raise I to the I power, it takes on a very dramatic meaning. And so this is an infinite set of, on the graph here, I to the I, far from being some sort of a complex number, is actually let me just write it down. It's an infinite set of points here. It's whatever e to the minus pi over 2. So that's, I don't know, a quarter or something. So 1 is out here somewhere. It's this, and then it gets knocked down to these small values. And so there's an infinite sequence that converges to 0, and they're all points that equal I to the I. So that's quite amusing. And if we do the same thing for minus I to the I, then we have e to the I, and now we have the natural log of minus I. Well, the natural log of minus I is 3 pi I over 2, so that's e to the minus 3 pi over 2. But you can write this more generally, because you can write minus I as e to the 3 pi I over 2 plus 2 pi ni. And now you again get this infinite sequence of points here. So that's, I think it's, that just goes to show that, you know, you just have to keep straight what it is that you're talking about there. All right, now what I'd like to switch to now, I think, let's see, I think I'm first going to do a couple of examples. One is an example 7.18. So let me get this off the screen and go to example 7.18. So now I'm switching to differential equations. Well, let me collapse this. Differential equations, and I guess it's the exercises 7.8, right? So we've got here a voltage applied to a resistor, in series with a capacitor, and right, resistor in series with a capacitor. And so the picture here is, let me switch to black then. So 7.8. And so the picture is that we've got a voltage here. And actually, I just drew it as a battery. That I don't think is the right symbol. Actually, I don't really know what the right symbol is, so I'm going to write it this way. That's the resistor. This is, oh God, that's awful. All right, let me do it this way. This is a capacitor. And now that's the, okay, so it's a resistor R, capacitor C, and a voltage V. So what's the equation? Well, V is equal to IR plus Q over C. And now if we take the time derivative of that, we get V dot is equal to I dot R plus Q dot. Well, Q dot is I over C. Okay. So we can rewrite that as, keeps, okay, I dot plus I over RC is equal to V dot over R. And so in the language of the general solution, which, let me get you back to the general solution. I think it was, oh, yes, it was over here. So the general solution is this. If we use this nomenclature, R and S, and then R is just a constant, 1 over RC, and S is a function. It's V dot over T, which we're given, divided by R. And so then if we just plug this in, well, what's alpha? Alpha then is the integral of R. R is a constant. So alpha of T is, apart from an overall factor that doesn't matter, it's, and a stroke that was a mistake, it's exp of the integral up to T of R, but R is just 1 over RC. So this is just e to the T over RC. So that's what alpha is. And once we have alpha, our general solution is y of T is 1 over alpha. So that's e to the minus T over RC times whatever the current is at time 0, plus an integral from 0 to T of e to the T prime over RC. Well, that's this thing here. We know what this is. This is just what I just got, e to the T over RC, or T prime over RC. And then it is V dot of T prime over R, that's the source function, dt prime. And so what is that then? The statement of the problem, I think, was that the current was 0 at time 0. I don't have the exercise in front of me, so let me switch to exercises. And it was, yes, the current at time 0 is 0. So that simplifies this thing a little bit. Namely, it's just e to the minus T over RC times this integral. And the integral is 1 over R, 0 to T, e to the minus T prime over RC, V dot of T prime, dt prime. But we're told actually what V is. Namely, V is V sine omega T. So V dot of T prime is just V omega cosine of omega T prime. And so this thing altogether is e to the minus T over RC, V omega over R, integral 0 to T, e to the minus T prime over RC. And now the rest of this is cosine omega T prime dt prime. Okay, well, with a sufficiently good big integral table, one can just work that out. I did it with my fingers, and I set this equal to then the cosine, of course, is of theta is e to the I theta plus e to the minus I theta, all divided by 2. So this is omega V. Actually, that V doesn't look very good. Omega V over 2R e to the minus T over RC. And so now we're integrating 0 to T. And now we have two factors, e to the T prime, 1 over RC plus I omega. And another one that's e to the T prime. Actually, it's e to the minus T prime, isn't it? No, it is e to the T prime. 1 over R. Wait a minute, I have e to the minus T prime. Well, all right, let me try to get this in my paper notes, I have alpha is right. Yes, this should be a plus here. That's what it was there. So it's a plus there. It's a plus here. And so we have just T prime 1 over RC plus, and then 1 over RC minus I omega. And then we integrate dt prime. And these are the two. Well, those are two exponentials that are very easy to do. And so what we get is omega v over 2r. Let me collapse some of this and make it a lot bigger so that you can see it more easily. So doing these two integrals, what we get is e to the minus t over rc. And then the first integral is e to the t 1 over rc plus I omega divided by the coefficient here, which is 1 over rc plus I omega. And the other one is similarly e to the t 1 over rc minus I omega divided by 1 over, damn it, it switched to, it switches to eraser at the, whenever I touch it in ways that it doesn't like. All right, well, maybe we shouldn't use up a great deal of class time actually simplifying that in steps. Let me just say that you can rewrite this as omega VC over 2, 1 plus omega squared r squared. That's a squared. So let me. R squared C squared. And I unfortunately keep defaulting to a lowercase c because that's the speed of light, but it's the capacitance squared. And then what's left there, well, what's left there is, I'll do two steps, minus 2 e to the minus t over rc plus 2 cosine omega t plus 2 omega rc sine omega t. And so the final answer as I make it out, that I get is omega vc over 1 plus omega squared r squared c squared cosine omega t plus omega r sine omega t minus e to the minus t over rc. So that's the solution that I get to problem 7, 8. So let me put this aside. And I thought I would also do 7, 12. And I think I did that in Matlab. So let me, as I said, I was doing so many different things here today that, okay, so I thought I could, what do I have to do? I scroll up and then scroll down? All right, well, I'm missing that. So all right, well, all right, let's try to do hold on, let me just, to do that, let me just do Here, let me look up the MATLAB script. I think I'll just redo the MATLAB script. And so it was number 12. So let me just get to 12. There's 12. Okay, there it is. All right, so let me then show you how to do that using MATLAB. And I think this will be instructive to do this problem using MATLAB. So first you say sims y of t. And then you say ODE equals diff y comma t equals exp minus y. And if you just hit return, it just repeats what you said. Then you say, you give it a boundary condition. Condition is y of 0 is 1. And it repeats that to you. And now you actually ask MATLAB to solve it for you. So what I did was write y sol of t equals, now the y sol I think was just my choice, but then we say desolve, that's a MATLAB code word, ODE comma cond. So that's telling MATLAB to solve the ODE, which you defined up here. The ODE is dy dt, or minus dy dt is e to the minus y, which is this expression here. Somehow, I now see that the solution that I wrote down, oh, where did this minus sign come from? All right, the minus sign was a typo that I just made. So, well, let's continue with this version and then we'll do the correct version. And so there is the solution. And this is a funny sort of solution. The solution is log of e to the 1, which is just e, minus 1, minus t. So the solution that it's giving for this case, in other words, if the differential equation is y prime, or let us say y dot actually, y dot is equal to minus e to the minus y, then and y of 0 is equal to 1, then the solution is y of t equals, and it's the log of e minus t, which is a kind of weird expression. Let's now change the ODE. So let's say ODE equals this now. Oh, Jesus. What did I do? I need to undo that. Good Christ. All right. So let me just redo it. So I'm going to grab this ODE and get rid of the typo. And now getting rid of the typo, I'm going to say that. And now I'm going to say condition. Well, I can keep the same condition. I think MATLAB remembers everything. So I'm just going to say, I'm just going to say y sol to see if it gives me a different answer. No, so I have to restate everything. So we've got the ODE correctly. So I'm going to say y. Well, let me give the condition again, just in case. So cond equals y of 0 equals 1. And then I'm going to say y sol of t equals d solve ODE, comma, condition. And there's the answer. Now it's t plus e to the 1. And so the answer is, for this case, y dot equals e to the minus y. The solution is, let me move this over so we can both see it. The solution is y is equal to log of t plus e. So it's similar to the previous solution, which was e minus t. Now it's e plus t. And I guess one of the clever students figured that out as I was typing it. So let's see, that was that problem. Okay, we only have 9 minutes left, so I'm going to switch to something that I found really amusing today. Why is that there? So let me go back to Matlab here. Is that Mat? No, that's QuickTime. Where is Matlab? Oh God, there it is. Okay, so let me pull this down. If I what? All right, here is an example, and this was an example that was in this chapter on differential equations, and it was systems. Remember, we were doing systems of ordinary differential equations. And what I said was, suppose we look at this system. X double dot is minus rx, x squared minus a squared minus g x y squared, and y double dot is minus ry, y squared minus b squared minus g y x squared. So what you can do here is you can say that x1 or x3 dot is x1, x4 dot is x2, and then x1 dot is this, and x2 dot is that. And what has happened here is that x1 is y dot, x1 is x dot, x2 is y dot, x3 is x, and x4 is y. So that's what this seemingly autonomous system means. And so here's a trajectory, and I will just show you that trajectory by just running this thing. And you see, MATLAB gives you this thing, which I've just shown you. Suppose, though, that we change the parameter g, which describes some of the nonlinearities here. So let's change, instead of g equals 1, set g equal to 0.1. So we've reduced the nonlinearity in the part that couples x and y. See, these other terms, this is just x with x, and this is just y with y, but this is the coupling term between x and y. We run this, we get something totally different, which I find that just fascinating. And I'd recommend that you take this code and play with it. You can download it from GitHub. You go to my GitHub and you can find it there. Let's run it for even less nonlinearity. Good God. Boy, I did not expect that at all. Suppose now we go to more nonlinearity. Suppose we go to 2. And if we go to even more nonlinearity, to 10, say, see, it's just so amusing what happens when you fool around with these things, because the computers are just so good, my gosh, at solving them. It's just quite amazing to me. So suppose we go to just a half. It's as I said, it's just I think absolutely. In fact, I mean, these answers are so strange that I even wonder whether there's a bug somewhere, because how the thing can change. Let's put 5, 5, say. Just amazing. So I'd recommend that all of you play with this. In fact, what I'm going to do, in case you can't, easily get my in case you can't get my GitHub webpage and so forth, I'm going to send you so 468 Matlab code, and it's related to example 6.4, example 6.36. All right, I'm going to mail you guys this, and you can see the problem that it purports to solve. The solutions are so incredibly sensitive to G that I just wonder whether there's a bug somewhere, that maybe I coded the problem incorrectly, or the Matlab desolve doesn't work, or something else. But honestly, this is just a curious kind of behavior. If I run a slightly different value, I'm getting that. We go down to say 2.5. I mean, it's in a sense, it doesn't look like any kind of a bug that I can see. And well, obviously I can't see whether there's a bug here. So suppose we do 05. Just amazing. It just really is, I think, pretty strange. This is the transition that I find most bizarre. So let's sneak up on it. Let me go to 9 because we're running out of time. Ah, so you can see that it's turning into what we expected. Oh, no, it's not. All right, suppose I make it 02. Boy, there's a transition there from, so suppose we make this not, we make it 1.5. Well, we can see a sort of continuous transition, but it's really, really, really weird in my opinion. I don't know. So, oh, I was going to do one more problem. I tell you what, I was going to do 738 in detail, but we are out of time. So what I'll do is I'll do 738 tomorrow as a first thing in class. And so that might be useful for you. So I've sent you the code. You can pull up Matlab on your own and run it and tell me if there's some mistake in my code, or you think there's something crazy about Matlab or bug in Matlab, or if you think, well, it's just in systems of simple systems of nonlinear differential equations can exhibit absolutely surprising behavior. And I hope that's what it is, rather than a bug in Matlab or a mistake on my part. All right, well, I'm going to end the class now. So I'm going to stop sharing and stop recording. Does anybody have a last minute question? Like maybe just shout it out or type it on the chat session. All right, so I'm going to just end then. Goodbye, everybody.